All right, we're at part 3. We're just going to do a couple of examples, and I'm going to ask you to submit some things via Schoology. So that those instructions should all be in the assignment. All right, so our first example that we're going to talk about is a rock of mass m that's launched straight up in the air with an initial speed v naught. So the picture that I have shown is basically snapshots of its trajectory. It's not a projectile going like that. It's simply just going up and coming straight back down again. These are just snapshots of each point along the path there. So it's not a projectile launched at an angle. It's just going to go straight up, straight down at the very top of the path. That's where it's going to have zero energy. Our system is going to be the rock plus the earth. So we can understand that we're going to have kinetic energy associated with the rock and gravitational potential energy associated with the earth. Graphing, always an important thing in this unit. So we're going to do a quick sketch of the energy versus vertical position graph. So if we kind of remember that gravitational potential energy is proportional to the height, then we know for this one, it's going to start at a lowest possible point, and its gravitational potential energy is just going to be a linear relationship that carries up. So this would be our gravitational potential energy. Understanding that kinetic energy is proportional to the v squared, which is also proportional to the change in height, again from kinematics. Kinetic energy is also going to have a linear relationship with the change in vertical position, but it's going to start with a lot of speed and go down low. So it's going to start here and come back down to zero at the same point, and that would be our kinetic energy, which tells us that the total mechanical energy should be conserved. So the purple line would represent the total mechanical energy. Again, I probably shouldn't have added that part of the line here, but we can kind of see the conservation. Again, we're looking at a position versus energy graph. All right, to model it, again, we're going to use our bar graphs, and we're going to use gravitational potential energy and kinetic energy. No air resistance, so we do not need to worry about any dissipated or internal energy happening here. And I'm going to start with 4 full units of kinetic energy as the rock is launched straight up in the air. Then when it gets to this halfway point here, and I don't know if this picture is drawn to scale, but let's just say this is about halfway. So halfway up, it's going to have half as much kinetic energy as it has as what it started out with. So half of the energy is going to be transformed from kinetic energy into gravitational potential energy. We'll call this one position 1. We'll call this position 2. We'll label them here so we know what it's coordinated with. And then position 3 would be the ball at the very top of its trajectory. It has no speed because it's launched straight up in the air and then comes back down. That would be different from if we actually had something that was launched up in the air, because remember, it's still going to have some initial horizontal velocity at the very top of the trajectory here. You'll need that for one of the weather sign questions that's going to be coming up. Mechanical energy is conserved. That's kind of a big idea that we can see from our bar graphs. And any kind of loss in kinetic energy is going to be equal to any gain in gravitational potential energy. And we've modeled that as saying that the change in kinetic energy is going to be equal to the negative change in gravitational. So, but in this case, kinetic energy is decreasing. Here, this would be increasing, so you'd have a negative, and you would get a positive change in gravitational potential energy. If we looked at it as our graph as a function of time, so let's do another graph here and look at energy as a function of time. The time to the top, if we go from bottom to top, we know that gravitational potential energy is going to be proportional to that y height, which is going to be proportional to t squared. If we remember from kinematics, because this is constant acceleration, we have that 1/2 gt squared. So our gravitational potential energy is going to look parabolic like that. So that would be our gravitational potential energy. I probably should use the same colors as I used before. And then kinetic energy, which is going to be proportional to v squared, is going to also be proportional to t squared. Again, for constant acceleration, if you remember, we have this kinematic equation. So that also will look parabolic in nature. So then we'll see the kinetic energy kind of be parabolic the other way. That would be the kinetic energy. And of course, the total mechanical energy I'll draw the top here, that would remain constant and conserved. So again, note the difference between the time graph as opposed to the energy versus position graph. One is linear and one is parabolic. So we do need to always make sure of what is being graphed on that horizontal axis. All right, so here's some time for you to work. We're going to determine an expression for the maximum height. I will get you started and then I'll ask you to pause the video and to finish it up. Whenever we're asked to determine, or more likely that word is going to be derive or calculate an expression, you need to start with a statement of physics, and that is also the expectation on your WebAssign. So I could start with something as simple as the mechanical energy initial has to equal the mechanical energy final. I could write it out and say my initial gravitational potential energy plus my initial kinetic is going to be equal to the finals. That's also acceptable. Again, it takes a little bit more writing, but as we get more and more complex, you may want to start out with a full statement. And again, make sure that you write that full statement before you start plugging in the variables. So we're going to derive an expression for the maximum height, h max, that the ball will reach in terms of our given variables. Our given variables are m for the mass of the rock, and the initial launch velocity is v. And then you can do the same for here. Again, you would also include fundamental constants like baby g, gravitational field strength. So pause the video, revisit this, solve it, and turn it back on and we'll go over it. All right, hopefully you are back onto it, and I'm going to switch over to the solution. The expression for the maximum height here, again, you want to show your substitution of your variables here. So I have m, I put v naught in squared for my initial kinetic energy. My final potential energy is going to be mg h max, and I have 0 final kinetic energy at the top. Again, now just solving for h max, and I get v naught squared over 2g. So note, it's the same result as the kinematics. You will find very often, now that we're kind of learning about energy, that you don't even have to use kinematics much anymore, especially for constant acceleration. If you did not like kinematics, you can use energy now. There is no requirement that you have to use kinematics for solving for speeds or anything. In fact, it is often recommended anytime you have to solve for speed, use energy. It's usually going to be way easier. And it might be a little uncomfortable at first because this is new, but as you get more into it, you'll find that a lot of people never, ever go back to kinematics again. So that's kind of a nice thing. All right, determine the expression for the speed of the ball at halfway up. Again, so referring to those positions, position 1 was our initial starting position, position 2 was halfway up. We write kind of a statement of energy here. So my initial kinetic energy is equal to the final halfway up plus the gravitational potential energy halfway up. I substitute in variables into the equations. I don't skip steps here. The next step is to cancel the masses because they are in each one of those terms, which should make us happy because mass never matters when we're in free fall. I'm going to get rid of all those 1/2 by multiplying through by 2. And I end up with this simplified version here. Again, it kind of looks like the kinematic equation, but not exactly because there's a factor of 2 that's missing there, so don't shortcut here. Using our answer from the previous part, the definition of h max, I'm plugging that in, and then solving for the final speed. I get the final speed is the initial divided by the square root of 2. So notice I'm at half the height, but it's not half the speed halfway up. In fact, it's v naught divided by the square root of 2. It is, however, half the kinetic energy. So we have to kind of be mindful of the difference between half the speed and half the kinetic energy. All right, heading back to example number 2, we're going to go through that one together. For the pendulum, because a pendulum has what I call the pendulum shortcut, that we need to make sure that we have a really solid understanding of the change in height of a pendulum. So I'm going to zoom in again. We have a mass of 1/4 kilogram. We have a length here. We have a pullback angle. I'm probably going to do this all. In fact, let's just plan to do this all in terms of variables. So m, l, and theta will be the variables that we're going to use. Of course, we'll use baby g. Our system is going to be a closed system, so we will include the pendulum plus the Earth as our system. All right, So we're going to start out with kind of, as this thing is swinging, what's the maximum speed of the pendulum at the bob here? So as it kind of swings through this system, you cannot use kinematics because this is not constant acceleration. Hopefully we kind of figured that out from our units in circular motion, as we see that tangential acceleration varied as the sine of the angle. So we cannot use constant acceleration to kind of figure out speed, but energy makes this so easy because energy doesn't care about direction, just looks at the change. So we would start out with kind of our initial mechanical energy, which would be at position 1, is going to be equal to the mechanical energy at the bottom of the swing. So you're going to have initial gravitation plus initial kinetic, and then final gravitation plus, oops, that should be kinetic, final. So our initial kinetic energy is going to be equal to 0. I'm going to release it from rest. We're going to make gravitational potential energy be equal to 0 at the bottom of the swing. So we have our mg, kind of our initial height position, is going to be equal to 1/2 m maximum speed at the bottom. So this business here is really what's going to be the key, is kind of figuring out what is that maximum height. So I'm going to zoom in on my pendulum here so that we can see this a little bit more clearly. So when I look at this, I'm going to switch colors here. I'm going to make this my 0 position here. So this is where gravitational potential energy is going to be equal to 0. This is my y height. So essentially this piece right here is my change in height, which is going to be equal to y. This is how much my gravitational potential energy is going to change. So this is where we have to use a little bit of trig to figure this out. So I'm going to switch over colors again. So if I kind of draw this line right to the top of the pendulum here, this represents the length of the pendulum. This is also the pendulum string, and this also represents the length of the pendulum. Now, if I create a line right here, I'm going to switch colors again here. Okay. This is going to be our change in height of the pendulum. That's what we need to figure out. So again, if this is our pullback angle right here, and this full thing is the length of the pendulum, and I need to figure out this part, I just need to subtract this part from here. So that side of that triangle here, I'll switch colors again. Now I'll just stick with blue. No, here we go. This piece right here, let me go back to blue, is L cosine theta. This whole thing is L. So this tells me that the change in height of my pendulum is going to be equal to L minus L cosine theta. Now, this change in height of a pendulum is what I call my pendulum shortcut for dealing with energy. It's definitely something you want to memorize, but if you need to kind of draw yourself up the picture to understand it, definitely do it. But the change in height of a pendulum, you will use this a lot. All right, so this expression is what we are going to use in our derivation here. So we have mg L minus L cosine theta, parentheses around that whole thing, is going to be equal to 1/2 m v max squared. I'm going to cancel the m's, and I'm going to multiply by 2 all through it. So I am going to get, let's see, m's are going to cancel. I'm going to get 2gl 1 minus cosine theta is going to be equal to v max squared, and then I can take the square root. So we've got kind of our interesting relationship that we can figure out the maximum speed at the pendulum, and then of course we could connect that to the centripetal acceleration, and we could also kind of figure out the tension in the string if we knew the weight of it. So we can definitely connect this to our circular motion unit. And we will do that. So just kind of be mindful of that. All right. So we have an expression that we've derived based on a pendulum. So I want you to do kind of a quick experimental design. So using our pendulum apparatus, students are asked to experimentally determine the value of G. So what kinds of things would you need to measure? What equipment would you need? What would you need to graph? And then specifically, how would you determine G? So I want you to take a few minutes to think about this question, and I will put this up on Schoology so that you can enter your answers in your response for your experimental design. All right, that will finish up the lecture for today. I would like you guys also to try WebAssign questions 1 through 3 as your homework for tonight. All right, have a good one, guys. Bye. Trying to stop this there.